Hello, my name is Jose Vela, and this is my screencast video for my differential equation class. Overall, I thought the problem wasn't terribly difficult. If you made like kind of like a picture and you knew what was going on, it was actually pretty simple and it was easy to set up the differential. So the problem says that a man-made lake initially contains 200 gallons of water with 50 pounds of chemical dissolved into it. A solution containing 3 pounds of gallons of chemical runs into the lake at a rate of 4 gallons of water mixed with it. What is the maximum amount of chemical ever in a lake? So the three letters here are basically saying for us to set up the differential, and B is to solve it, and then after solving it, we could find out the maximum amount of chemical that was ever in the lake. So over here, I made a little drawing. It basically tells you how much water is coming in and how much chemical is coming in. Over here is the lake itself. It already had initial 200 gallons of water, and then initial 50 pounds of chemicals. And then over here we have water going out, which is 4 gallons, and chemicals going out, which we don't know. And then going on to my how I solved it. So I said that X would be chemicals, and then T is time, so it's gonna be chemicals over time. So we're gonna have to find out the differential of that, and we're gonna equal it to the input of water and chemicals coming in minus the output of water and chemicals going out. So the first step is to solve for input. So the way to solve it is just you're basically going to multiply chemicals coming in and then water coming in. So we got 12 pounds per minute. And then the output is going to be the change of chemical over water. So we don't know what chemical was because in that graph I showed you that was unknown, but we knew what water was. And then so basically we had 200 gallons of water in the lake. So we just divided that by 4 from what was going out. So we got 50, and we don't know X chemicals, so it's going to be X over 50. So we're just going to put that into my equation up here, and then we get the differential is dx over dt plus 1 over 50x equals 12. So that's A. So now we're going to have to solve for it. So we're going to use the integrating factor method. And then when we do that, like, then when we do it, it's going to be e to the integral 150 over dt, and that's just going to be equal to e to the t over 50. And then over here, we're going to multiply um, x times the integrating factor, and then that's on the left side, and then on the right side, we're going to do the input rate times the integrating factor. So on the left side, we're just going to do the product rule. And then when we get the product rule, it's just going to be x e x to the 50. I don't know why I have this little mark right here. And then on the integral side, we're going to do the integral of e to the t over 50 times 12. But 12 is just a constant, so we could take that out. So we just do the integral of e to the t over 50. Then when we do that, it's going to be e to the t over 50 divided by t over 50. We just use u sub right there. So now we get this differential. It's y equals 600 plus c e to the negative 1 over 50t. And then now we're going to solve using that what we know is t equals 0 and then x equals 50. So we're going to multiply it here. And then we're going to 50 times e to the 0 equals 600 e to the 0 plus c. And then we get that c is equal to negative 550. So we're just going to plug that up into this equation, and then we're going to get 600 minus 550 e to the negative t over 50. So that's our differential. That's the equation we're going to use. And so now we have to solve for the maximum. And to solve for the maximum, you could do like the algebra approach like this, or you could just know that, like, since it's the chemical will eventually run out, so it's gonna be 0. Like this right side, it's eventually just gonna go to 0, and then you're just gonna have 600 by itself. So we could say the max amount of chemical in the lake at that time was 600. So there you go. Thank you.